reason that the variance of a sample differs from that of a population is easy to understand if you look at the calculations the right way. In part 1 of this video, we considered a population consisting of all of the Smarties in a certain box, and we weighed each Smartie so that we could calculate the population mean and variance. We then took a sample consisting of 3 Smarties from the population. The mean of that particular sample was higher than the population mean, but its variance was less than the population variance. Here's the reason that population and sample variances differ. The population variance is the sum of the squares of the distances, shown here in green, between the data points and the population mean mu. However, the sample variance is the sum of the square distances, shown in red, from those data points to their mean. One can show mathematically that the mean is the very point that minimizes the sum of those square distances. So the reason that a sample variance is smaller than a population variance is because the square distances are measured to a point closer than the population mean mu. If you calculated the sum of the square distances shown in green between the sampled points and the population mean, a considerably larger sum would have resulted. That sum would usually give a better estimate of the population variance. In practice, we usually do not know the population mean, and so we cannot use this approach. If you experiment with the variance calculator spreadsheet by moving some of the points around using the sliders, you can check these claims by comparing these two boxes. If we make the sample size larger, the sample gets closer to the population mean. The distance arrows get longer and closer to those associated with the population mean, and the bias decreases. From the theory of random variables, we know that on average the sample and population means will differ by sigma over square root n. Parts 1 and 2 of this video have shown that sample and population variances are different from each other. Is there a way to mathematically relate one to the other? The answer turns out to be yes, as we will see in part 3.